And one thing I wanted to mention to you is that I guess I have good news and bad news for you. And I'm going to give you the bad news first. That is that the first half of this lecture is going to be very mathematical. That's, of course, necessary because we're going to talk about inverse square law and also some basic statistics of medicine. But the good news is after this first hour, there will be very minimal mathematics for the remainder of the lectures that we have to go. So the worst is almost over, as they like to say. So let's take a look. We're going to start with the inverse square law. I like to tell my classes that the inverse square law is really your best friend. There is nothing you can do quicker, simpler, cheaper to protect yourself from radiation than simply move away from the source. And it's not a linear relationship, as the name of it implies. It's a squared relationship. So here's what the inverse square law says. The intensity of a point source, and I define that for you on the bottom here. A point source is a source where radiation is being emitted in every single direction from a really small volume. For example, a small light bulb with a little filament in it, or the tip of a radio or a television tower, or a little dot of radioactivity. Those are good point sources. A 4-foot long fluorescent light bulb is not a good source. It might be if you're 100 yards away, but if you're close up, which we always are for measurements, then that would be a bad point source. So here's what the law says. The intensity of a point source varies inversely with the square of the distance. So inverse refers to the subscripts. Watch what happens here. I1 is to I2 as D2 squared is to D1 squared. The 1 and 2 would match up here if it were a...
Dr. Karish?
Yes.
I'm sorry to interrupt you, but I don't know if you're sharing your slides or not. I don't know if you're screen sharing yet.
I'm sorry. Hold on. I think you're totally correct. Let me go back here for 1 second. Okay, is that better?
Yes, thank you.
Okay, good. I'm so sorry. I forgot to turn the share screen on. Okay, so I'll repeat that so you can look at it. I1 is to I2, and we're going to invert the subscripts as D2 squared is to D1 squared. And the mathematical beauty of this is when you cross multiply, look what you get. I1 D1 squared equals I2 D2 squared. Here it is on the next slide. And that's very easy to remember. An intensity times its distance squared equals the other intensity times its distance squared. And that's what this says down here on the bottom. And so I'm going to jump ahead for 2 slides just to show you a problem and how you can set this up in your head. If the intensity number 1 is 100 and D1 is 1 centimeter, you're simply going to say 100 units times 1 centimeter squared equals I2, the unknown, times 10 centimeters squared. And here's what that looks like right here. 100 times 1 squared is I2 times 10 squared. So you really, if you understand that, you don't even need the formula here at all. You're simply going to take an intensity times the square of its distance. That will always equal the other intensity times the square of its distance. Now here's a pictorial that might help to put this in perspective for you. Here's a point source, and while it's irradiating in every single direction, we're just looking at it as the radiation is going off towards the right. And you can see here, if we go from the point source to the middle of this box, we're at 1 meter, and the reading is 40 intensity units. If we go out to 2 meters, we have doubled the distance, but remember, this is a squared relationship, so it's not going to drop by 2, it's going to drop by a factor of 4. And so have we lost any energy or not? The answer is no. We still have 40 intensity units in total, but look what happened. It's distributed over 4 boxes instead of 1. So the intensity went down by a factor of 4. So here's the easy way to think about this. If you double the distance, the reading drops by a factor of 4. If you triple the distance, it drops by a factor of 9. If you quadruple the distance, it drops by a factor of 16. If you go from 1 meter to 10 meters, it's going to drop by a factor of 100. So very often you're able to work these problems in your head. Truly, some of them are very easily workable in your head. So let's take another look at this problem. And please take out your scientific calculators or your cell phones. And there are two keys that you would like to locate. One is the x squared key for squaring numbers, and the other one is the square root key. So please make sure that you can find those two keys, x squared and square root. So this little stick diagram is pretty helpful because all you have to do is take the top times the square of the bottom. That equals the other top times the square of the bottom. 100 times 1 squared equals I2 times 10 squared. So in this problem, we're going to work it in our head. We went from 1 centimeter to 10 centimeters. We are 10 times as far away. The reading has to drop by a factor of what? Anybody? If you're 10 times as far away, the reading drops by a factor of
4.
not 4. Remember, it's a square relationship. It's just going to be 10 squared,
100.
100, right? Remember, if you doubled it, it dropped by 4. If you quintupled it, it dropped by 25. And if you go 10 times as far, it's going to drop by a reading of 100. And here's the proof of that. Here's your math. 100 times 1 squared is I2 times 10 squared. Now, here's where I would like you to take out your calculator. And here are going to be your keystrokes. 100 times 1 x squared key divided by 10 x squared key equals. And that will give you 1. And you'll see that the reading dropped from 100 to 1 exactly as we predicted because we went 10 times as far away. And conversely, if we go 10 times as close, the reading is going to go up by a factor of 100. Now you'll have a little bit better feel for this after we've worked a couple more problems. Anyone having any keystroke problems? Okay, since I don't hear anything, I'll assume that you found those keystrokes okay. So here are a couple of problems that I put together for you. And this first one, what you really need to do is pay attention to the units. On an exam, as I mentioned last week, it's very common for units to be mixed up. So this says we have a reading of 100 at 1 centimeter. So you know that the first half of your equation is going to be 100 times 1 centimeter squared. And the other reading, I2, will be I2 times this. Now, 1 millimeter, 1 centimeter, we have to get them in the same units. So if we're going to use centimeters here, then 1 millimeter is going to be 0.1 of a centimeter, a tenth of a centimeter, because a millimeter, that's what a millimeter is. It's a tenth of a centimeter. So here's your math. 100 times 1 centimeter squared equals I2 times 0.1 of a centimeter squared. If you don't correct for these units, you're guaranteed failure. So we would solve for I2 as follows. 100 times 1 squared divided by 0.1 squared. Give the keystrokes a shot right here. 100 times 1 x squared key divided by 0.1 x squared key. And that should give you 10,000. Remember, the initial reading was 100. We moved 10 times as close. The reading is going to go up by a factor of 100. 100 times 100 is 10,000. Okay, let's take it number 2. Now this one has no change in units. So we are first going to work this in our heads, and then we will work it on the calculator. We have a reading of 287 MR per hour. The distance is 1.5. What would the reading be at a distance of 15? So we have gone 10 times as far away, right? From 1.5 to 15, we're 10 times as far away. The reading is going to drop by 100. 287 divided by 100 is 2.87. That's working in our head. And here's the math. 287 times 1.5 squared equals I2 times 15 squared. Here's your equation. I2 is going to be this times this divided by this. Here are your keystrokes, 287 times 1.5 x squared key divided by 15 x squared key. And then you must punch equals. And that, of course, will give you the 2.87. Okay. Now, that's solving for intensity. That's pretty easy compared to solving for distance because we have to take the square root, and that's not so easy to work in our heads. Before we go to problems 3 and 4, any questions about problems 1 or 2? Anyone? Okay, let's take a look at problem number 3. Here we have a reading of 287 at a distance of 1.5. So we know by setting up our equation, it's going to be 287 times 1.5 squared equals 28.7 times d2 squared. We don't know the distance. Here is the setup. 287 times 1.5 squared equals 28.7 times d2 squared. Now, if you solve for d2 squared, you don't have your answer because that's d2 squared. All you want to know is what is the distance. So you're going to have to take a square root. So here's the setup. The last thing you want to do is press that square root key. But look what's under this huge square root line here. You're going to take 287 times 1.5 x squared key divided by 28.7 equals. That's going to give you a number, I'll take a guess, it's like 22 or 23 or something like that. And then you're going to press your square root key, and that should give you 4.74. All right, everybody okay on that? Any questions? Problem 4 is basically the same problem. I just changed some units on you. Lumens per hour is a measure of visible light. So the light in the room where I'm speaking from right now has a certain number of lumens per hour, or it might even be lumens per square centimeter. It doesn't matter too much what the units are. So here we have a reading of 12 lumens per hour at 3.5 centimeters from a point source. At what distance would the reading go from 12 to 100? Now, if it went from 12 to 100, it went up by a factor of, almost 90, probably 88 or 90. So the distance has got to be very small, probably less than 1, I would take a guess. So here's the setup. 12 times 3.5 squared, that's right here, is 1,000 times d2 squared, that's right here. If we solve for d2 squared, all under the square root sign, we're going to have 12 times 3.5 x squared key divided by 1,000 equals, and then we have to hit the square root key, and the answer is 0.38 of a centimeter. So if we go from 3.5 centimeters to 0.38, you can see that we're, we've gone down by a factor of, let's see, a factor of 10 approximately. Okay, any questions about problem 3 or 4, anyone? I'm going to show you 2 more exam questions. They're both right off of old exams, and they're related to what is called the gamma ray dose rate constant. And you'll see very shortly why inverse square law plays a big part. This gamma ray constant or gamma ray dose rate constant uses the Greek symbol capital gamma, the very first symbol right here, capital gamma. And it really is giving you the strength of a point source. It represents the dose in rads delivered by a 1 millicurie point source if held at a distance of 1 centimeter for 1 hour. So you can see the units are always rads times centimeters squared per hour times millicurie. Let's say if this were 5 in front of this, then that means that if we held the source 1 centimeter away and the source is a 1 millicurie in activity, and we held it there for 1 hour, we would get a reading of 5. Okay, pretty easy to understand that. But what happens when the numbers are not 1, 1, and 1? For example, what if the constant is this right here, 5 R centimeters squared per hour millicurie, but we're holding it 5 centimeters away from a 5 millicurie source for 5 hours. Now, if you get that problem on the exam, here's my advice. Don't panic. It is not a hard problem. All you have to do is take this constant right here and multiply by 5 millicuries, 5 hours, over 5 centimeters squared, and just make the units cancel. It's really simple. Look at this. Here's your constant. Hours in the bottom. So we're going to multiply by 5 hours. Hours cancel. Millicuries in the bottom. We're going to multiply by 5 millicuries. Millicuries cancel. And look what's in the denominator. You might think, let's divide by 5 centimeters. But number one, as we move from 1 centimeter to 5 for a point source, this is an inverse square law problem. Yes, it's a little bit more complicated than the others. That's all it is. And anyway, if we didn't square the 5 centimeters, the units wouldn't cancel. And so here we have this 5 squared cancels this 5 and this 5. Everything else is canceled. And the answer is going to be 5R. So remember, if you see a question related to this kind of constant, you just make the units cancel. It really is pretty easy. Now, let's take it one step further. Same kind of problem, but number one, in this problem, it gives you the millicuries and it gives you the distance, but it does not give you the time. And so we're simply going to have an answer in terms of R per hour. We're not going to have any time unit to cancel that R. The answer is going to be R per hour. Now, here's the difficulty in this problem. We're going to work it just like the one we just did, but the constant is an R, that's rads, but I asked you what would be the dose rate in MR per hour. Now, if you don't convert it to MR, there's a really good wrong answer right here that you would get, and you'd be wrong. It has to be converted to the same units so that are requested here. So once we get the final answer in R per hour, we're going to have to multiply that by 1,000 to get MR. So let's take a look at the solution. We set it up exactly the same way. Here's our constant. We're going to multiply by 6 millicuries. Millicuries cancel. We're going to divide by 8 squared centimeters squared. This is an inverse square law problem. Centimeters squared cancel. So all the units are canceled except R per hour. So here's what we've got. 1.65 times 6 divided by 64. And that comes out to be 0.1547 R per hour. Now, let me back up. There's that answer right there. It's a wrong answer because I didn't ask for R per hour. I asked for MR per hour. So if we have to take this number and to convert it from R to MR, we have to multiply by 1,000 because a millirem is 1,000th of a rem. And so 154.7 is choice B, and that will be your correct answer. Okay, we are going to leave inverse square law, but before we do, two things. Number one, I want to remind you that these problems are very common on the board exam, number one. And number two, many of them are really answerable just logically without even using a calculator. Okay, any questions about inverse square law before we leave that topic? Anyone? Okay, good. We're going to take a look then, we're going to shift gears here. We're going to take a look the basics of medical statistics. Yes, you're likely to get a question or two on that on your exam. And I'm going to give you a general overview of statistics. I am by no stretch of the imagination an expert, but I do know what the basics are. And I also know a little bit about what they've asked on prior exams. So let's take a look. I am assuming by now that you know less than or greater than, less than or equal to, greater than or equal to. If you don't know those by now, I have to say you're probably in trouble. But these are a little bit more difficult. We have a lot of Greek letters here. This is the capital letter sigma, the uppercase sigma, and it represents the summation function. It's the sum of all the iterations that are going to follow. This is also sigma, but sigma lowercase is the standard deviation. And to put that in one simple word, it's really the error involved in measuring something, whatever we're going to be measuring, the error involved. X bar is the mean value. I might have asked you this last time, and let me hide this for one moment. What is the difference between the mean value and the average value? Anyone? If you have a series of numbers, you calculate the mean value. What happens if you calculate the average value? Anyone? Okay, so it turns out they're exactly the same. The mean value is the average. We have 10 numbers, we add them up, divide by 10. That's the mean, and that's also the average value. Here's one that people mix up with the mean value. That is the median. The median value is the middlemost value. Now, let me give you a couple of examples. If we have these numbers, 1, 2, 3, 4, 5, we add them up, divide by 5, the average value will be 3, which is also the median value. But what about these numbers? 1, 2, 3, 4, 9. 3 is still the median value. It's still the one in the middle, but it is no longer the mean value. So the mean and the median are sometimes equal, but most of the time they're totally different. The mode is the most frequently occurring value. For example, if I have this series of numbers, 1, 2, 3, 3, 3, 4, 5, 3 would be the mode, the most frequently used value. Let me bounce back up a little bit. N is the frequency. Really, it means how many times do we count a sample? N equals 10. We counted a sample 10 times. And we'll see some examples of that shortly. And very finally, the chi-squared value is actually a dimensionless number. It has no units going to it. And well, I'll show you later at the end how we might calculate that, but it's pronounced chi-squared. And it's a measure of, they like to say it's a measure of the goodness of fit. How well do your measured values and the standard values correlate with each other? It's important to know. It's especially valuable in assays like radioimmunoassays, where you're measuring samples in duplicate or triplicate, and then the chi-squared value is truly very useful. So those definitions you need to know. I would say probably almost all of them are important. Now, I want to go through 3 more definitions before we take a look at some mathematics. We want to define and have an example of accuracy and precision and reliability. And the problem, accuracy is pretty easy. The problem with precision is that we use incorrectly in our everyday life. You know, when we say, look at your watch and you say it is precisely 9:26, the implication is my watch is right. That's not scientifically, that's not what precision means. Precision simply means that we have reproducibility. So let's take a look at the definitions. Accuracy is the correlation between the observed and the true values. For example, you have a dose calibrator, you have a 100 microcurie source, put it in the calibrator, and you take a couple of readings and look at the values, and they come out to be 99.5. That is a very accurate calibrator. It should have given you a reading of 100. You got 99.5. You'd be lucky to get that close. So accuracy means that your measured value and your standard or calibrated value are equal. That's all that accuracy means. Did you get the correct answer? That's what accuracy means. precision in one word is reproducibility or consistency. It's not really even connected to accuracy. For example, if you have a dose calibrator source, it should read 100, and you took 3 measurements, and here they are, 64, 63, and 64. Do we have precision? Yes, we do. That's very reproducible. 64, 63, and 64. Very reproducible. But do we have accuracy? And the answer is totally no, because the average value here is around 64, but it should have been 100. So here we have precision, but no accuracy at all. And so the final definition is going to be reliability. And this is the condition that exists when both accuracy and precision are within some number of limits. For example, on a dose calibrator, all the dose calibrator tests have limits of plus or minus 10%. So a dose calibrator is reliable if the constancy test, that's your precision, is within 10%. And it's also reliable if the accuracy test is within 10%. So a piece of equipment of any kind is reliable if you have both accuracy and precision. We say in everyday life, my friend is reliable. What does that mean? That means my friend does the right thing all the time. So very important to have reliability, and you only have it when you have both accuracy and precision. So keep in mind the precision is unrelated to accuracy. It simply means reproducibility. Okay. Now, we're going to take a look at the mathematical application of statistics, but we're not going to do really tough things like students paired t-tests and anything like that. I'm not saying it's real easy, but we're not doing high-level mathematics for statistics. So the first thing I want to do is define for you sigma. Lowercase sigma is the standard deviation or the error involved in measuring something. And for a single event, we've counted one sample one time for 1 minute. For a single event, here's the formula. All we can do is take the count rate and take the square root of it. For example, if you have 10,000 as your count rate, and you want to know the error is going to be plus or minus 100. That's the square root of 10,000. Now, this is only applicable if you're counting one time. If you're counting a series of times and you have n is some other number like 5 or 10, you've counted it multiple times, then we have a totally different formula, and we're going to take a look at it. And in fact, I took this question off of an old exam. Which of those 3 formulas is the correct formula for sigma for a series of events? You've counted a sample multiple times. Now, this, if you look at A, this is in every one of the formulas. This is the sum of the squares of the deviations. The deviations mean we take every single individual value, we subtract from it x bar, you'll recall that's the average value, and we get our deviation. And then we divide the sum of all those deviations by n minus 1. So here's your question. Is it A, with no square root sign? Is it B, where the square root is numerator only? Or is it C, where the square root is over the entire formula? Anyone like to hazard a guess?
Is it C?
It is, in fact, C. That's totally correct. There it is. For a series of events, the sigma is plus or minus this value. We're actually going to work a problem like this, or at least I'll work it and show it to you. It's not hard at all. It truly is not, but you have to know how to do it. But the math is really simple. Now let's go back here. We said for a single event, the error, or sigma, is plus or minus the square root of the value. That would be the count rate. So so we want to take a look at how do we calculate percent error. Now, I want to derive this equation for you. It's really not very hard. Sigma is the square root of the number, and it's the error. So if you take the error of that count rate and divide it by the count rate, you come up with the percent error. Remember that sigma is the error. It's the square root of counts. So if we substitute square root of counts for sigma, look how easy the formula is. Percent error is going to be the square root of your count rate divided by your count rate times 100%. The bad news is you really have to memorize this formula unless you understand how to derive it, but it's pretty simple. Percent error will be the square root of counts over counts times 100%. For example, let's say we counted a sample one time for 1 minute, we got 10,000 counts. What will be our percent error? It's going to be the square root of 10,000 divided by 10,000 times 100. So if you'll take out your calculators, you want to punch in 10,000 square root key divided by 10,000 times 100 will give you 1%. Now, here's the reason I chose 10,000. The rule of thumb in a hot lab is that anytime you're counting something in a well counter, let's say chromatography strips, not microcuries or millicuries, but a few 100,000 counts, you want a minimum of 10,000 counts on the coolest piece of your strip, because then you're guaranteed to be counting with a percent error of no more than 1%. You'll see shortly that as the count rate goes down, the percent error goes up pretty dramatically. And as the count rate goes up, it also goes down. The percent error goes down dramatically. So simply the square root of counts over counts times 100%. Now, let's take a look at a much harder problem for setup at least. The math is easy, but setting up might not be. Let's say you have a percent error of you want to count with a percent error of less than 0.1%. The count rates therefore have to be greater than some number. We're still going to use exactly the same equation. We're going to say that this percent error equals square root of counts over counts times 100%. Well, here's the setup. Percent error, which I gave you as 0.1%, is equal to square root of counts over counts times 100%. All right, let's start this way. Percent signs cancel. So now we have 0.1 equals square root of counts over counts times 100. If we divide both sides of the equation by 100, this cancels. 0.1 becomes 0.001. And this looks like a very simple equation. 0.001 is equal to the square root of counts over the counts. Here's the algebraic problem. Your unknown is at two different powers. Here it's a square root power at the 1/2 power, and here it's at the whole power. And by far, the easiest thing to do is square both sides of this equation. This side, 0.001 squared, here it is. This side, the square root of counts times the square root of counts gives you counts. Counts times counts gives you counts squared. One of these cancels one of those. And so we have 1 over the count rate is equal to, this is 1/1,000,000th. So the count rate will be 1,000,000. Now, here are the keystrokes. If you take a look down here on the bottom, remember the unknown, the counts, is in the denominator. So, this is the inverse. So all we have to do is square this number on your calculator, 0.001 x squared. And then you just want to turn it upside down. Remember, this is 1 over x. So if you press your 1 over x key, it'll convert 0.000001 to 1,000,000. So the setup is identical to the previous problem. The algebra is a little bit more difficult, but if you square the whole equation, it becomes a pretty simple problem. Okay, any questions about either of those? Anyone? Okay, now let's use that large formula that had the sum of the squares of the deviations over n minus 1. Let's say we have a 10 millicurie dose calibrator source. And I'm going to ask you a question now, and I want an answer from somebody. You counted that dose calibrator source 5 times. You counted it, took it out, put it back in, counted it again 5 times. Here are your readings: 12, 11, 10, 9, and 8. Here's your simple question. Do you like that dose calibrator or not? You want that dose calibrator in your lab? Anybody?
No.
No.
You definitely do not. That's good. Definitely not. Look, your average value here is 10. These values, 11 and 9, are they're 10% off. That's already, you're at the legal limit. And 12 and 8 are 20% above and below. This is a terrible dose calibrator. Is it accurate? Yes. If I add all these up and divide by 5, I get exactly 10.00. It's accurate. But what can you say about precision? Terrible, right? You don't have good precision here. You have 0% error, 10% error, and on these two, 20% error. That's terrible. So we have a accurate by accident dose calibrator that is totally imprecise. Now, the mean value, well, remember, we're just going to add these up and divide by 5. The mean value, that added up to 50. The mean value is 10. We want to remember that so we can plug that into the formula. So when you work a problem like this, all you need to do is set up 3 columns. Here are the counts. We want to subtract X bar, the mean value, from each individual value. So look, if the mean value is 10, we're going to say 12 minus 10 is 2, 11 minus 10 is 1, 10 minus 10 is 0, 9 minus 10 minus 1, and 8 minus 10 is minus 2. Do these two numbers, which are negative, does that negative sign bother you? The answer is no, because you're going to square it and they're going to disappear. So here are our deviations. Here are the squares of the deviations. 2 squared is 4, 1 squared is 1, and so on. We simply, remember what that formula said, we sum the squares of the deviations. So if we add up 4 and 1 and 0 and 1 and 4, it comes out to be 10. Now let's plug that in. The sum of the squares of the deviation is 10. We use n minus 1. There were five values. We're going to just use n minus 1, which is 4. And we're going to simply say 10 divided by 4 is 2.5, and then hit the square root key. And the square root of 2.5 is 1.58. So here's what we've got. Mean plus or minus sigma. That's the same as mean value or average value plus or minus the error is 10 plus or minus 1.58. Now, if that is the case, if this is your mean value and this is your error, what would be the percent error of that mean value? How would we calculate the percent error? Here's the value. Here's the error. What would be the percent error? How would we do it? Anybody?
Would it be 1.58 divided by 10?
Perfect. That was terrific. Look, there it is. We take 1.58, that's your error. We divide it by the value of 10, and that calibrator has a standard error of the mean of 15.8. And that's why you didn't like that dose calibrator. You eyeball the numbers and you could say, I don't like it. Some were 10 and 20% off, but this is the real value here. The percent error is almost 16%. What's the legal limit? 10%. And if you're really close to 10%, you probably have a dose calibrator problem. You could continue to use it because it's legal, but this, you could never use something like this. Okay, good. Now, how do you know, let me back up for 1 second. How do you know whether to use n or n minus 1? Now, I don't have a really good rule of thumb, and I'm not a statistician, but what they generally say is if n is a large number of iterations, if you counted a sample 25 times, it doesn't matter if you use 25 or 24 in the denominator. It won't make any difference at all. But if you count it 5 or 4 times, it makes a difference. So some people just use n minus 1 all the time. But if n is a very large number, like 25 or 50 or 100, then you could simply use n. but using n-1, you can never go wrong. Now, any questions about the mathematics so far? Okay, good. I think you've all heard of the famous bell-shaped curve, and that's called a Gaussian distribution. What it is a curve where the distribution of values around the mean value is symmetrical. And here's what a Gaussian distribution would look like. And the bad news is that sometimes on the exam, they expect you to know this number and this one, not the bottom one. But if they ask you what percent of all values for a Gaussian distribution falls between mean plus 1 sigma and mean minus 1 sigma, that's this large white area in the middle, the value is going to be 68.3%. There's nothing intuitive or logical about it. You just have to memorize that number, 68.3%. If you include under the curve this striped area on both sides, this large white area, then that would be all of this area here, and that would be 95.5%. And here, if you have mean plus or minus 3 sigma, it's so close to 100% that it really doesn't help you much with statistics. But these two values are truly important, especially the 95.5, because you're going to see shortly what doctors do in medicine with 95.5%. So here we're going from mean value plus or minus 1 sigma, or mean value plus or minus 2 sigma, or mean value plus or minus 3 sigma. Okay, and you guys probably can see those numbers pretty well, but sometimes when you look at your course notebook, it's very hard to see them. So I simply put them here on the next slide. All values fall between mean plus or minus 1 or 2 or 3 sigma. Now, if you ended up with a problem that had 5 sigma in it, there's no formula to calculate that. It's simply what you calculate 1 sigma and multiply by 5. That's all. So there, as it says here, there's no formula to calculate 2 or 3 or 4 or 5 sigma. We just take 1 sigma and multiply by 2 or 3 or 4 or 5. And we're going to work a problem like that in a little while. Now, here's what I just mentioned about what doctors do with mean plus or minus 2 sigma. This could be a good exam question. I've never heard that it was on there before, but this is something worth knowing, even for your personal knowledge, if not for the test. Laboratories set their normal ranges for tests by using mean plus or minus 2 sigma. For example, let's say you wanted to know what is the normal range for calcium. You just had a blood calcium test. You want to know what the normal range is. You look it up and you find that it's 8 to 10, I think it's milligrams per deciliter, some number like this. Doesn't matter what that is. But where'd that normal range come from? They took 100 normal volunteers, took their blood, they measured it, they took the mean value plus or minus 2 sigma, and that's where that value came from. So the normal range for lab values for everything is set by taking normal volunteers and determining the mean value plus or minus 2 sigma. Now, let's go back and take a look at this. I mentioned 95.5% is an important number to note, and that's because mean plus or minus 2 sigma, the normal range, requires that 95.5% of all normal values fall within that range. Now, here's what's really important for you to know. 4.5% of normal people have outliers. They have readings that are not normal. I've had it happen to me before. I had a lab test. The doctor says, one of your values is slightly out of the normal range. Come back next week and let's repeat it. And I go back next week and it's fine. It's just one of those things that happens. You can only expect 95.5% to be within the normal range, even for people who are totally normal. So physicians have to be careful interpreting lab tests, especially if you're near the very low end or the very high end, because it might fall in that 4.5%. Now, Here's a math problem right off an old exam. Within what count range can we be 95.5% confident? How many sigma would that be? 95.5. How many sigma?
Two.
Two, right? And what is the error in counting? No, within what count range can we be sure that the percent error is 1%? Now that problem we worked 20 minutes ago, you might remember from the first problem, we said if it's 10,000 counts, we took the square root of 10,000 divided by 10,000, and that gave us a 1% error. So a 1% error means that we're counting with 10,000 counts. What would be the sigma for 10,000 counts? If we've counted a sample one time, sigma is going to be the square root of that number. So to be 95.5% confident, we're going to take the mean value of our count rate, that's 10,000, and add plus or minus 2 sigma. And so 100 counts would be 1 sigma, 200 counts would be 2 sigma. And so if we take 10,000 counts plus or minus 2 sigma, that will give us 9,800 to 10,200. That means that if we are in this range, we are 95.5% confident that we're counting with a 1% error. So mathematically, it's a double problem, because if you're told 1%, you have to back calculate and determine this number and then do this math. Okay. Now, this problem looks pretty easy. Everybody I know got this wrong. I got it wrong. Our physicist got it wrong. One of my bosses, one of the physicians got it wrong. And it's sort of misleading. Everything up till now, we've counted for 1 minute, but what if we count for 3 minutes? So first time I looked at this, I said, okay, the count rate is 300. The square root of 300 is around 17 or 18. I would take the 18 counts, divide by 3, and come up with 6. Turns out that is totally the wrong way to do the problem. What you have to do is determine the total number of counts collected. How many was that? 300 counts per minute times 3 minutes is 900. So we say, yes, we collected 900 counts in 3 minutes. The square root of 900 is 30. And 30 divided by 3 is 10. And that is the correct answer. In any case, you have to get the total number of counts. So if it's more than 1 minute, you may have to multiply by the number of minutes to get the total counts, and then divide it by the time. Now, this is a tough problem conceptually to understand. I'm going to try to clarify it for you. If a sample, you have a well counter, you put a sample in there, and the well counter says 9,000 counts for, let's say, 1 minute. And then you count background for 1 minute, and it's 1,000. Now, I think everyone agrees that the net counts would be 8,000. Okay, there's no question that's correct. Sample count minus background is net counts. That would be 8,000. This says calculate the sigma of the difference. I'm sorry, I thought I had turned that off. So here we have a difference of 8,000. This problem has a very unique and totally unpredictable way to solve it. You would think that we could just say, okay, the net count rate was 8,000. Why don't we just take the square root of 8,000? But look, let's go back. Was there an error in counting 9,000? Yes, there was. We know that. 9,000 is almost 10,000. That means the error is going to be a little bit over 1%. Here, at 10,000, that's going to be the square root of 10,000, I think is about 31.6. This is going to be a 3.2% error. This is a 1% error. You cannot assume that the errors are going to cancel each other out. In fact, you know they won't. They can't possibly. And so you have to keep in mind that an error could be plus or minus. And so what we have to do is take the counts that we got, plus the background counts that we got, add them up, then take the square root, and you get 100. This is probably the most counterintuitive problem I've ever seen for statistics or almost anything else. But you have to remember that every individual count that you took had an error, both the count rate, the counts and the background, and the error could be a plus error or a minus error. And so in this case, we take the worst possible case condition, we add these up and take the square root of the total. Okay. The worst is over. We're finished with the math now. Any questions about any of that math before we continue? Okay. There are a couple of terms that are related to curves, statistical curves. There's a curve called, a term called skewness, is a curve skewed to the left or skewed to the right. Now let's take a look at this curve over here on the top left graph right here. The way to determine which direction of skew is you go up to the apex of the curve, you drop a vertical. That would come down just like this. And so you'll see that there's more area under the right than at the left. So this curve is skewed to the right. Or look at this curve. If you drop the vertical right here, straight down, you've got a much larger area to the left than the right. So if you just look at this and say, oh, this curve looks like it's leaning to the right, it's not skewed to the right, it's skewed to the left. This is the famous bell-shaped curve, the Gaussian distribution, which has no skew at all. It's totally symmetrical. If you drop a vertical down here, the area under the left equals the area under the right. So be careful with the skewness. I'm going to give you one of these on our practice exam in a few minutes. Modality has to do with values that appear the most commonly. For example, if we were to plot the population in the United States as a function of age, maybe there are more people who are your age and my age than any other age. And so these are modes, and this is called a bimodal curve because there are two modes. Or maybe there are more people who are 25, especially 50 and 75 than any other value. That would be a multimodal curve, or you probably could get away with calling it a trimodal curve, I would imagine. So any questions about skewness or modality? Okay, good. Now, let's say that there are 3 dose calibrators, A, B, and C. And you can see that curve A is narrow, curve B is wide, and curve C is extremely wide. These have identical mean values. You can see that they're all symmetrical curves. So the mean value, if you drew a straight line down from A through B through C to the bottom, they all have the same mean value, but different sigma. Which dose calibrator do you want in your lab? A or B or C?
B,
Which one?
B.
B? I don't think so. You would want, you want the smallest standard deviation you could get. Let me give you an example of numbers where you would generate a curve like this. Let's say you have a dose calibrator source that's 10 millicuries, and you read it 3 times, and you have values of 9.5, 10, and 10.5. That might give you curve A, where you have a small deviation. How about curve B? You might have, let's say it's a 100 microcurie source. You put it in the calibrator and you got the values of 75, 100, 125. Add them up, divide by 3, you got 100. Accurate? Yes. But is this consistent or reproducible? The answer is no. Is it precise? Not at all. And curve C, you might have for values of, for where the value should be 100, you might have read 50, 100, 150. So curve C has a huge standard deviation. So the precision is terrible. Here it's very close to terrible, and here it would be excellent. So you want the smallest sigma you can get for your dose calibrator, and that would of course be curve A. Now, the chi-squared value, you are very unlikely to get a question on this, So I'm going to kind of race through it in just about 1 or 2 minutes. As I mentioned before, it's the goodness of fit. How well do your measured values and the standard values fit? You'll note that this looks a lot like sigma. It has the sum of the squares of the deviations in it, but two things are different. Number one, there's no square root sign. And number two, instead of n minus 1 in the bottom, it's some mean value. So the important thing to note here, though, is it does sum up the deviations. And so if the deviations are small, chi-squared is going to be a small value. If the deviations are large, chi-squared will be a large value. Let me give you a couple of examples. Let's say that you ran a few standards. The standard values are a 0, 1, 2, 5, 10, and 20. You measured 0, 1, 2, 5, 10, and 20. All your deviations are 0. Your chi-squared is going to be 0. Now, what about this? Let's say your values were 0, 1, 2, 5, 10, and 20, and your values were 0.1, 1.1, 2.1, 5.1, 10.1, 20.1. All your deviations were tiny. They were only 0.1. If you take a bunch of 0.1s and square it and add them up, you've got a very tiny number. Your chi-square is going to be very, very low. But what about the following? You have 0, 1, 2, 5, 10, and 20, and you got 3, 5, 16, 43, 57, and 200. Your deviations are huge. Your deviation squared are enormous, and chi-squared is going to be off the charts high. So the smaller the deviations are, that is, the more consistent or precise your values are, and also accurate, the lower chi-squared. And what do you want? You want the lowest chi-squared value that you can get. Now, there, in all good statistics books, there are what are called the chi-squared tables. You simply calculate the one for your assay, look up your confidence level, that is it 95.5%, and you compare your chi-squared value to what's in the table. If your value is less than in your table, your assay is valid. If your chi-squared value is higher than what's in the tables, then you've got a problem. You've got a large deviation between your standard and your measured values. And so that would make it undesirable. All right, I'm going to skip a couple of these. I think I'm going to skip actually all of those. Let's take a short test. Most of these are true or false, but a couple of them we should be able to solve pretty quickly. We made a measurement one time, 2,500 counts in 1 minute, counted one time. If 2,500 is the count rate, what would sigma be? How many counts would sigma be? What's the square root of 2,500?
50.
50, right? So if the count rate is 2,500 and sigma is 50, then you want 2 sigma, because 2 sigma is this number here, 95.5% correlates to 2 sigma. So we're going to say 2,500 plus or minus 2 sigma. That would be 2,500 plus or minus 100. That would give us 2,400 to 2,600, and that would be the correct answer. Okay, everybody follow? Okay, take the number, figure the square root, double it to get 2 sigma, and then add and subtract that number, the 2 sigma, to this 2,400 to 2,600. Okay, and here is the here's the math for you. I'm not going to grind through it, but you won't have trouble following it. Okay, these are true, false. I'm counting on somebody to yell out an answer. Reliability depends upon the agreement of observed and true value. True or false?
True.
That is true, because the correlation between true and actual, between observed and true values, is the definition of accuracy. Let's go down to E. Accuracy is the correlation between observed and true values. That is true. That's why A is true. Reliability depends upon that agreement. B, reliability depends upon reproducibility.
True.
True. That's precision. So if we have an accurate and precise instrument, gives us the right answer almost all of the time, then that's reliable. Precision is a measure of reliability and accuracy.
False.
False.
False. Precision is a measure of one thing, reproducibility. Accuracy, D, accuracy is a measure of reliability and precision.
False.
False.
False. Accuracy is, and that's false because E is true. Accuracy is a correlation between the observed and true values. Good. And there are your answers. How about this one? The mean value of a series of numbers equals the sum of the individual values over n, where n is the number of times you took the measurement.
True.
That is definitely true. You sum up your values, divide by n, that's your mean or your average value. B, the mean value always equals the median value. Remember, the median is the one in the middle.
False.
That is false. Could they be equal?
Yeah.
Sure they could, but they usually are not. So using either always or never, you know how they say never, and probably never say always is also a good thing to keep in mind. Okay, C, the standard deviation is represented by this formula if you've counted a number of samples.
False.
False. What's wrong with it?
The square root.
Square root all over.
Right, square root is not over the entire thing. That's what makes it false. Okay, that curve at the right is skewed to the left.
False.
False.
That is totally false, because if you go up to the apex of the curve and drop a vertical down to here, the area under the curve to the right is enormous compared to the left. Good. Okay, here's some more. For a Gaussian distribution, the bell-shaped curve, 78.3% of all values fall within mean plus or minus 1 sigma.
False.
False.
False. Should be
68.3. Yeah.
good. 68.3, not 78.3. Okay, F. The lower the value of chi-squared, the better the correlation between expected and measured values.
True.
That is true. Remember, you want the lowest chi-squared number you can get. The lowest you could ever get is 0. We never expect to get 0. That means your assay is 100% perfect. No lab values should be perfectly measured perfectly like that. Okay, G, mean plus or minus 2 sigma is used to set the normal range for lab values.
True.
True.
That is definitely true. Okay, now we're actually running right on time. And let's just take a mental breather. Any questions from anyone about anything we have covered before we dive into modes of decay? Anybody? Okay, I'm going to forewarn you that the modes of decay lecture is probably technically the most difficult one for concept. It's got a lot of information in it. It's really not very simple at all. And what we're going to do is methodically go through each of the modes of decay, take a look at equations that apply to them. Then we're going to look very closely at decay schemes, and we're going to especially note in which direction does the arrow in the decay scheme go. If it goes down to the left, that's one mode of decay. If it's down to the right, that's a different mode of decay. So we want to concentrate on all of that. So again, this is not simple. I'm going to try to go not too fast. And please, if there's anything you don't understand, please just give a shout out, let me know, and I'll explain it again if necessary. Okay, modes of decay. You all know from not just what I taught you in lecture number 1, but what you learned in chemistry, maybe physics, that nuclei contain nucleons. You'll recall that nucleons would be the sum total of the protons and neutrons in the nucleus. And certain combinations of those are stable. Stable means not radioactive. A lot more of them are unstable, and something is either radioactive or not. There's nothing in between. It is either stable or unstable, but there are some degrees of instability. For example, you could say Potassium 40 is almost stable because the half-life is 1.3 billion years. You could say technetium is very unstable because the half-life is 6 hours. Okay, so that kind of qualifies it a little bit, but still, they're all radioactive. So we have protons and neutrons, and the combinations of those nucleons will help to indicate whether something is going to be radioactive or not. What we're going to focus on here, especially in this first part, is two things. The neutron-proton ratio, that is key to understanding the modes of decay, why they take place, and how they take place. Also, a less important thing is called the even-odd rules. Are the numbers of protons even numbers or odd numbers? And by far, the most important thing here is the neutron-proton ratio. Is it too high, too low, or is it just right? And so one of the things I want to mention here is that because nuclides differ so much in their ratios and in the evenness and oddness of the numbers of nucleons, there are various modes of decay. You should not be surprised that there's more than one mode of decay. For example, if a nucleus is what we call neutron excessive, it has too many neutrons per proton, it's going to decay in a certain way. If it's neutron deficient and it contains too few neutrons per proton, it's going to decay totally differently. So you should not be surprised that there are several different modes of decay that we're going to look at. Now, I want to make sure that you all are clear on the term radioactive, because people think that radioactivity is only causing things to be emitted from a nucleus. And believe it or not, that is not true, because there are nuclear events that take place in the nucleus that eject electrons. Those electrons leave a vacancy, a higher up electron drops down to fill the vacancy, and characteristic X-rays and Auger electrons can be emitted. So if it's radioactive, here are the things we need to know. Number one, it's spontaneous. We can't start it. We can't stop it. We can't accelerate it. We can't decelerate it. We have no control over radioactivity, we humans, nothing we can do. And so these are spontaneous radiations, but take a look at this. They can come from the nucleus itself, and they can also come from alterations in outer electron orbitals. Their configurations can be changed, as I mentioned earlier, by having an electron knocked out. And so we'll take a closer look at that a little bit later. But just keep in mind that radioactivity can cause things going on in outer orbitals, such as X-ray production, characteristic X-ray production, and also Auger electron production. And so let's take a look. First of all, this is simply a guess on your part, unless you happen to know the answer. There are almost 3,000 known nuclides. What percent of them do you think is stable or not radioactive? I'm going to give you some choices. 10%, 30, 60, or 90. What percent of all known nuclides is stable? Anyone? Good.
90.
Maybe, that's right. It's not even 10%. It's more like 8. And the number of known nuclides is approximately, I think it's 2,850 something, and only 257 or some number like that are stable. Now, this is a chart out of a book called The Trilinear Chart of the Nuclides. It was published by the Mallinckrodt Corporation, and this chart must be 30 years old, maybe more. And the color coding, I don't know the whole color coding system, but here's what I do know. The black ones are stable, and every other color is a different time unit. I'll make this up, like pink might be seconds, and yellow might be minutes, and green might be hours, and red might be days, and some other code like that. So if you follow along, you can see that the black ones going up and going more and more, there aren't that many of them. It's, as I mentioned, about 8%. Now, I need you to follow the pointer here. The reason this chart is split in 3 is that instead of having a normal book, you'd have to have a book about 4 feet wide or maybe 3 feet wide and only 4 inches tall. So if you follow the pointer, this left-hand edge here is hooked on to the right-hand edge over here. And near the bottom, this left-hand edge is hooked on to the right edge over here. So what you have is one really long graph that is gently sloping upward. It's a very gentle slope. It's not rocketing upward. And it's also not a linear line, you'll see shortly. Now, if we take a look at all the radiations resulting from radioactive decay, every one we could think of, believe it or not, they fit on one slide. Look what we have. Alpha particles, helium nuclei. We have beta particles, which could be plus or minus, positrons or negatrons. We have electromagnetic radiation like X-rays coming from outer orbitals and gamma rays coming only from the nucleus. And this is not a minus sign here. This is gamma hyphen rays and X hyphen rays. That's not a minus sign. There are internal conversion electrons that result from radioactive decay, and there are Auger electrons. So we have a lot of particles. All these are particles, and all these are particles down here. And only number 3 has radiations that are electromagnetic, like X and gamma. So everything fits on one slide for the types of radiation. Now, we're going to take a close look at the neutron-proton ratio. That's the most important factor. We'll take a quick look at the even-odd rules. We're going to ignore the binding energy. Now, everybody calls these the even-odd rules. Rules usually are applicable most of the time, if not all of the time. That's not at all the case here, not even close. And so I think about them not as a rule, but as a trend. If you had to take a guess, this would help you to guess the right answer. But you'd be off, you and I would both be wrong a very significant percentage of the time. So first, let's look at the even-odd rules. Here's what it says. If the number of neutrons and the number of protons are both odd, you can expect instability. Now, let's look down at the bottom of the slide here. There are only 4 known nuclides out of 279 stable nuclides. Only 4 of them are odd. For example, deuterium is hydrogen 2. That's H112, odd numbers, 1 proton, 1 neutron. Deuterium, that's deuterium. Lithium is 336, 3 protons, 3 neutrons. Boron 5510, 5 and 5 are odd numbers. Nitrogen 7714. We're breathing that right now. 77. Those are the only 4 odd combinations known out of almost 3,000 nuclides and out of 279 stable nuclides. So, and then let's go back up to the second bulleted point. Out of these 279, 200 of them are even. So we have 200 that are even. We have 4 that are odd, and that means we have 75 that are either odd even or even odd. And we can't really make much of a prediction there at all. So look, if you had to predict these, oxygen 8816, you would say, okay, even, I'm going to predict stable. Fluorine 19, odd. Not only would you predict stable, but how does fluorine 18 decay? What's the mode of decay?
Positron emission.
Hmm?
Positron emission.
Sure. It's a PET agent, right? F18, FTG, and other compounds. Sure. So F18 is 99, odd, unstable. We would have predicted that correctly. But look at this one. This is fluorine 9, 10, 19. This is the fluoride that you brush your teeth with every day. It's odd even. And your prediction would be a big question mark. You don't know. Happens to be stable. Helium 3 is even odd, and it's questionable stability. It also happens to be stable, but you have no way to predict it. So the only time you can really make a decent prediction is if it's even, stable. It's odd, odd, unstable. So I'll show you, I don't think I have a slide for it, but let's take a look at this example. Just think about this in your head. You have uranium 92-238. Is that going to be, what's your prediction, stable or unstable? 92-238. The number of neutrons has to be an even number, correct? So this uranium-238, 92-238, that would be even. You would predict it's stable. It's not. No uranium is stable. So uranium 92, 236, 234, 232, 240, 242, those are all even. All of us would be totally wrong. That's why I don't like calling them rules. It's a trend. But if someone asks you to predict, these are the two where you're going to be able to make a prediction. Okay, I don't want to overdo the even odd rules. They're not that important. They don't appear on exams that often. This is just a chart I found that's just showing you a couple of the examples. I already showed you those two right there. Now we're ready to dig in with the neutron-proton ratio. If you recall this slide right here, if we were to take every one of these 2,800 nuclides and plot the number of protons versus the number of neutrons, we would come up with a graph that looks like this. We plot neutrons versus protons. This yellow line is referred to as the band of stability. That is where it's totally stable. You'll note that it is not linear. It doesn't come out on this straight line where n equals p. That works great for the first 8. H11, helium 22, lithium 33, beryllium 44, boron 55, carbon 66, nitrogen 77, oxygen 88, fluorine, oxygen 88. Up to there, it'll be a straight line. And after that, number 99 is unstable, and 1111 is unstable, and 1313. So this line is a stability curve. It's gently sloping upward. And so now follow the pointer. This huge triangular area right here, this whole big blue area above the curve, is referred to as the neutron excessive region. Point A is a randomly chosen point here. It does not mean there are too many neutrons. It means there are too many neutrons for the number of protons. You just have, it's neutron excessive. Now here's what has to happen to bring it back to stability. If you're up here at point A, you have to lose a neutron and gain a proton, and that will bring this back to the region of stability. Often it happens in one step. Sometimes it takes 2 steps, but that's what has to happen. So, and the only mode of decay that can go from neutron excessive to stability is beta minus decay. That's neutron excessive. And so how do we lose a neutron and gain a proton? So a neutron breaks down into its component parts, which are a proton, which stays in the nucleus, an electron, a beta minus particle, which is emitted. And so we have lowered the NP ratio because a neutron converted to a proton. We lost the neutron, we gained the proton, excuse me, and we have achieved stability. This large triangular area down here is called the neutron deficient region, where the number of neutrons per proton is too low, simply too low. And so what has to happen is that a proton has to convert into a neutron, excuse me. Number of protons goes down by 1, the number of neutrons goes up by 1, and we have achieved stability. Again, might take 1 step, might take 2, but that's what has to happen. So we have 3 regions here. Region 1 is the band of stability, very narrow. And as you saw, not many fall into that band. And then we have this huge area of neutron excessive and this huge area of neutron deficient. Now you'll note this line of n equals p that only worked up to about number 8. And after that, the line zigged and zagged a little bit. Now it's not a smooth curve like this. I think I put yeah, so if you look at this curve, here they have plotted it a little bit differently, but you'll note this black zigzag line going up. Those are the stable elements. So you can see what the trend of the curve is, but you can also see it's zigging and zagging all over the place. Way up here, this color is alpha. Down here, you're most likely to get positron decay. And up here, where it's neutron excessive, you're most likely to get beta minus decay. Let me just see if I skipped anything. I don't think so. So if you get a question that says, what's the trend of this curve? It just increases, the number of neutrons increases somewhat greater than the number of protons. What that means is you go from number 20 to number 40 to number 60 to 80 to 100. The number of the neutron proton ratio goes up. Here, it might be 1.1. Here, it might be 1.2, 1.4, 1.5. Here, the neutron proton number might be 1.6. So it's gently sloping upward. It's just increasing somewhat greater than the number of protons. Okay, now, any questions about that diagram? This one here, anybody? Okay, we're going to go through the modes of decay one by one. And the first one is alpha particle emission. Truly, you're not very likely to get questions about alpha decay very much. There are a couple they do ask occasionally. You're most likely to get a question about beta minus decay. But let's look at alpha. It won't take long. An alpha particle, as you know, is a helium-224, 2 protons, 2 neutrons, and it's really a large particle. It has an atomic mass of 4. Compare that to an electron, which has an atomic mass of 0.0005 of 1 atomic mass unit. So for a nucleus to be able to eject an alpha particle, that nucleus has got to be big. It's going to have a Z number greater than 83 or a mass number over 200. If the mass number is under 200, alpha decay almost never, ever occurs. And so that's what this says, with very few exceptions. Nuclei have a Z number greater than 83 or a mass number typically over 200. Now, here is a decay of alpha emission. Radon, this is the radon that we're concerned about in the environment. Radon 222 decays to polonium 218 and produces an alpha. You'll note the math, 222 equals 218 plus 4. 136 equals 134 plus 2. The number of protons, 86, is equal to 84 plus 2. So when this happened, note what happened. It went from 86 to 84. It lost 2 protons. Went from 136 to 134. It lost 2 neutrons, but the impact on the ratio changed. It didn't change much, but it changed. We'll see a calculation shortly. So you'll note that, and here's an exam question. I think it's on my quiz for you. When alpha decay occurs, what happens? And the answer is the Z number goes down by 2, the N number goes down by 2, and the A number goes down by 4. Now, let's look at the math. This went from 136 over 86. That was a neutron-proton ratio, 1.58. Here, went from 134 to 84. That increased by a little bit. We expect that because alphas fall out in the neutron deficient region, and we have to increase the NP ratio. But unlike with betas and beta plus and beta minus, which takes 1 step or 2 to go to stability, that's not what happens here. This is a very small change, a little over 1% in the ratio. And so what you're going to see is multiple steps before it gets there. These are called alpha decay chains. There are many, many of them that are well documented. They have been well known since probably almost 100 years ago, 75 to 100 years ago. And here's what's happening. The parent decays to the daughter, which decays to the granddaughter, which decays to the great-granddaughter, to the great-great-granddaughter, and so on, until ultimately it reaches this stable area, and it's usually the element lead or sometimes bismuth, but most often lead. So This is down in the neutron deficient region, and you can see that the NP ratio is just going up slightly with every single transition. Every one of these is about a 1% increase. Now, we're going to study alpha decay, and here's the rule for knowing which direction to draw the arrow. You'll see that in alpha decay, the arrow goes to the left, always. Beta minus decay, it goes to the right, always. How do you make that determination? It's a simple rule. What happens to the what happens to the Z number of the daughter relative to the parent? If the Z number of the daughter went down as it did here, it went from 86 to 84. As the Z number goes down, the arrow goes to the left. And so all of these arrows are down to the left. They're all alpha decays. This is simply 3 different pathways of going from the parent to the daughter. So this is a case where the parent goes straight to the ground. Any gammas given off? Yes or no? For this pathway. So if you don't see a straight line coming down like those, there are no gammas. So in this case, the parent is going straight to ground, no gammas. That's going to be the maximum amount of energy. And for alphas, it's very often 5 or 6 or 8 million electron volts. Look at this middle line. This is a lower energy alpha going to this level. This is a metastable state of the daughter. And then what happens? It goes from here to ground. That little arrow there is an isomeric transition. It's going from this metastable state to the ground state. And then this arrow here is the probably the lowest energy alpha, and it's going to the highest metastable state of the daughter. We would say this is a highly excited daughter, this is an intermediate excited daughter, and this is the ground state daughter. So look what happens here. This goes to this line. Now you'll see this is an excited daughter. It has 2 ways to go to ground. It can go in one step and give off this big gamma, or you could get sequential isomeric transition, and you can have this gamma followed by this gamma. Now, here's the mathematical beauty of this. The energy of this alpha right here, going from parent to daughter, that's the highest value. The energy of this alpha equals the energy of this alpha plus this gamma equals the energy of this alpha plus this gamma equals the energy of this alpha plus this gamma plus this gamma. In other words, going from parent to daughter, no matter what pathway it takes, sometimes it's called routes or pathways, no matter what pathway it takes, the energy expended going from the parent to the daughter is a constant value. You add up each of those separate lines, constant value. So these are all drawn down to the left because they're all alpha decay. And we want to kind of keep that decay scheme in mind. Remember, we drew it to the left because alpha particles, when they're emitted, the Z number has dropped by 2. So it's going to the left. Now, let's say that alpha, this alpha right here, the big one, had 5.58 MeV. The energy of the alpha particle that we're going to measure is a lower value. And why is that? That's because there is something called recoil energy. And in this case, the recoil energy is not insignificant. It's 1/10 of an MeV. And so the particles that are traveling away have a little bit lower energy. Now, let me give you an everyday example. If you've ever fired a gun, if you fired a BB gun, you know, you got a teeny little pellet coming out, you are so big and strong, you can't feel the recoil. That's akin to an electron being ejected. The mass is so tiny that the recoil is almost 0. But an alpha particle being emitted is like shooting a cannonball. And if you've ever seen one of these Victory at Sea movies, when the cannonball is ejected, that huge gun moves back in its track 5 or 6 feet. Or a shotgun. Shotgun moves your shoulder back. The recoil energy is significant. It's the most significant in alpha decay, the least significant in beta minus and beta plus. Now, I'm not going to grind through this math, but this is conceptually what you need to know. Let's say that this radon is emitting an alpha particle in this direction. As the radon is doing that and being converted to polonium, it's emitting the alpha particle in this direction. So this alpha recoils and pushes the radon to the left as it's being converted to polonium. Now, what is the distance from the center of this circle to the center of this circle in measurement? It's probably micrometers. It's very tiny. You can never see it with the naked eye. You couldn't see it anyway, but it's very tiny. But there is physical motion that's involved. And so we call this an alpha recoil reaction. And every time that an alpha is emitted, the parent nuclide, as it's being converted to the daughter, recoils a small distance in the opposite direction. Okay. Any questions about alpha decay? Anyone? Okay. Next is beta minus decay. And this happens when the neutron-proton ratio is excessive or too large. And your exam question is something like this. What is the only mode of decay that can take place when we're in a neutron excessive state? And that is beta minus. Nothing else is neutron excessive. A bunch of things are neutron deficient, like alpha and beta plus and electron capture. But this is the only thing that's that where the NP ratio is too large. Now, here's an interesting question. In the first lecture, I asked you, what's the difference between a beta minus particle and an ordinary electron? Physically, they're the same thing. Beta particle is an electron. The only difference is that a beta minus particle is an electron emitted by a nucleus, whereas an electron can only be emitted from an outer orbital. So think about this. They call this a paradox. How many electrons live in the nucleus? 0. There aren't any. Only protons and neutrons. So if there are no electrons, how can a nucleus eject an electron if it doesn't have one? So look at the equation on the bottom. A neutron is converted to a proton. Now what happened? The neutron number went down by 1. The proton number went up by 1. That lowered the NP ratio. So converted to the proton, which stayed in the nucleus, and also it formed this electron, which of course is ejected. We call that a beta minus particle, an electron ejected from the nucleus. This little guy here is the Greek letter nu, which is a neutrino. And these two here are almost always emitted simultaneously, and they always share this energy. Not equally, possibly equally. The chances are 99.999% it's not an equal share. We'll take a look at a sharing diagram shortly, but let's review that. Neutron disappears, forms a proton, stays in the nucleus. The electron is ejected, the neutrino is ejected. These two share this total energy. Now, here's where we are. We're up here at point A in the neutron excessive region. And so we lost the neutron, we gained the proton, and the resultant brought us into stability. And so what happened to the number of protons? Did it go up or down? It went up, right? So what direction's the arrow in the decay scheme going? To the right or to the left?
To the right.
Right.
To the right, sure. If the number of protons goes up, it's got to go to the right. So here's a generic equation that really covers all beta minus decay. Element X has a Z, A, and N number, and look what it does. It goes from Z to Z plus 1. This went from N to N minus 1, but more importantly, the Z number always increases by 1. And look on the very bottom line at what happened to the NP ratio. It went from N over Z to N minus 1 over Z plus 1. That is lowering the neutron-proton ratio. And therefore, since it went from Z to Z plus 1, the arrow has to go to the right. Here is our electron. Here is our neutrino. Here is our energy, which these two are sharing. And so you can see that for all beta minus decays, Z goes to Z plus 1. Therefore, all arrows go to the right for beta minus decay. Now, here's a real world example. P32 is a very potent beta minus emitter. It decays to stable yellow sulfur 32. Look at this. 15 went to 16. Z number increased by 1. It emitted these two. They shared 1.71 million electron volts. The atomic mass remained the same. Now, here's a good rule for you. The atomic mass of the parent is always going to be greater than the atomic mass of the daughter, because all this stuff here didn't come from nowhere. It took some mass away from this. So this 32 is smaller than that one. In whole round numbers, they're always going to be the same. But this might be 32.050, and this might be 32.000. There's not much difference in them, maybe in the third decimal place. Now, let's take a look at the ratio. Now, remember when we did that ratio calculation for alpha decay, it only increased by 1%. But take a look at this. The neutron-proton ratio here is 1.13. Here, it's obviously 1. And so this is a drop of almost 12% decrease in the neutron-proton ratio. That's a huge percent. That's enough to take it to stability in one step. And that's exactly what happens here. P32 goes to stable sulfur 32. So that's a very large decrease in the neutron-proton ratio. Now, I just asked you this question. Let's see if you were paying attention. In this equation, the A associated with X is less than, greater than, or equal to the A associated with Y.
Greater than.
Great.
Greater than. It's always going to be greater than this one. It'll never even be exactly equal. This one will always be a little less. Good. That's been an exam question, by the way. Now, here in that decay of P32 to sulfur 32, we know the arrow has to go down to the right, and this one goes straight to the ground state. How many if 100 P32s decay to 100 sulfur 32s, how many gamma rays are given off?
None.
0. Correct. You don't see any vertical lines. That means there is no excited daughter. 0. And so when a physician injects P32 into a patient, that physician doesn't have to be really cautious about being dosed with P32, because all that's coming out are beta particles. Yeah, there are a few X-rays, but mostly it's all beta particles, and he has a lot to worry about with his hands if he's injecting, but not his body, because there are no gamma rays to expose him. So there are 3 nuclides for therapy. There's P32, there is strontium-89, and yttrium-90. And those 3 have an identical decay scheme to this because they are all pure beta with no gamma. Well, that's the nice thing about P32 as a therapeutic. We almost never use it anymore, but the dose rate to the dose administrator is just minuscule other than the hand dose. And even that's not bad if he works fast. Okay, now this is a simple decay scheme, P32, but look at this one. Many, many years ago, gold 198 was used for certain kinds of therapy. It used to be put into knee joints for relieving pain in arthritic knees. We don't use it for that anymore. But look at this. We have this beta going from gold 198 straight to the ground state, stable mercury. Any gammas given off in this transition or not?
Yes.
No, right? This is pure beta going from here to here, no gammas. But look at this one. This is a little bit lower energy beta going to this state. This is mercury 198M, but I put 1 star by it to indicate it's an intermediate excited state. This one would be at 2 stars, a highly excited state. So look at this. This goes 0.96. This goes here and then drops to 0.41. And the total here is 1.37. Look at this one, 0.28 plus 1.09 is 1.37. And so this shows you on the bottom, the mathematics, that no matter what path it takes, the total is going to be 1.37. And so there are 3 different gammas coming out. Do we like any of those gammas for imaging? The answer is no. This one is probably almost not imageable, over 1 million electron volts, 0.68, very poor imaging. 0.41, that's a little bit higher than I-131, also poor imaging. So we would not like to image with any of those at all. True or false? Alpha decay schemes, the more complex ones, mirror the beta decay schemes. They have mirror images of each other. So I'll show you a diagram and you can decide for yourself. This is a mirror image, the complex alpha decay scheme and the complex beta decay scheme. The only difference is that the lines here are going down to the left for alpha and down to the right for beta. And they all have these excited levels going to ground. Now, unlike alpha particles, which are monoenergetic, beta particles are not. In fact, they have a broad spectrum of energies. And so those energies vary from slightly more than 0 MeV up to the maximum energy for a particular isotope. If you use a very strong magnetic field, you can actually separate those betas out and spread it out and form a diagram that shows you the population of betas as a function of energy. And that diagram would look something like this. So here, we're starting at this fairly low energy. This is the beta. Now we're plotting population as a function of energy. So as the energy increases, look what happens here. As the energy increases from very low, the number of beta particles goes up and up and up and up and up. And then the number of particles peaks here. And then it starts going down and down and down and down and down. And out here at Emax, it drops to less than 1%. In other words, let me back up one slide. The literature value for a beta is Emax, even though not even 1% of all betas have maximum energy. This here is the average energy is somewhere up here. It's about 1/3 of Emax. And so this diagram is pretty easy to explain. It's a sharing diagram for betas and neutrinos. Let's take the first line here. This solid line here is the beta energy. And this dotted line here, this dash line, is neutrino. So here you can see there's a lot more neutrino and a lot less beta. Here it's an even smaller number of beta and more neutrino. But look what happens as the go out farther in energy. This line here is now an increase in energy of beta. So the amount of neutrino energy is lower. This is a huge amount of beta, only a little neutrino energy. And out here at Emax, we have 100% beta and 0 neutrino. But remember, that almost never happens. It's maybe 1% of the time. So this is called the sharing diagram. And you're simply plotting the population as a function of energy. The important thing to remember is that betas are not monoenergetic like alpha particles. Okay, any question about beta particle decay? If not, let's take a look at positron decay. Remember we said that occurs in the neutron deficient region where the NP ratio is too low. And what causes that is a proton disintegrates into a nucleus. Now, my training is as a chemist, and yes, I guess I know a lot of physics, but and I had a minor in that in college. But I love to tease the physicists about this because there's no logical and rational explanation. How can a proton convert to a neutron? Which is more massive, a proton or a neutron? Which is more massive?
Neutron?
A neutron, sure. If you wanted to go in your garage and make neutrons, what would you do? You would take a jar of protons and a jar of electrons and cram them together and make a neutron. Okay, not quite that simple, but you get the point that a neutron is approximately the mass of an electron larger than a proton. So number one, how can a proton form a neutron larger than itself? And number two, aside from the fact that this is larger than this. All this other stuff is also coming out. This 0 is not 0. It's a very small amount, but not 0. And all this energy and the neutrinos, all that are coming out. What we know is that this equation does explain the facts. It does explain positron decay, but it's just kind of hard to rationalize that proton can form something more massive than itself, plus other stuff. But we're going to assume that this equation is correct. So what happens to the neutron-proton ratio? Remember, positron, neutron deficient ratio is too low. We lost the proton, gained the neutron. The NP ratio went up. We were down here at point B. We lost the proton, we gained the neutron. The ratio went up and reached the band of stability. Now, this is a generic equation for all beta plus decays. We have element X with A, Z, and N numbers. And look what happened. This went from N to N plus 1. The ratio would therefore be N over Z going to N plus 1 over Z minus 1. Pretty obvious that the ratio is going up. The NP ratio is going up and helping to achieve stability. And look what's coming out of here. This is a positron. This is a neutrino. And these two particles, just like in beta minus decay, share all of this energy. They share this energy. Now, if someone asks you, which is a neutrino and which is an antineutrino, I have treated them generically like they're all neutrinos. That's probably the simplest, the best way to learn it. But if someone says, which is an antineutrino, here's how you should be thinking about it. Anti means negative. So a negative electron is associated with an antineutrino, and a positive electron is associated with a neutrino. So this is a neutrino, but the neutrino from beta minus decay was an antineutrino. Okay, so let's take a look at a real one. Zinc 65 decays to copper 65. The Z number went from 30 to 29. What direction is the arrow going? Left or right? Anybody? Went from 30 to 29. The Z number decreased, going to the left. And you can see that the ratio also is increasing. And here is the ratio. This went from 35 over 30, 1.17, to 36 over 29, 1.24. That is a 6% increase in the ratio. It's not a 12% increase like that one we looked at for beta minus, but it's also much bigger than the 1% we typically get for alphas. So this is often enough to get us there in one step. Now, what always happens when positrons are emitted? I think you've seen this diagram a number of times already. Positron will ultimately collide with an electron. They will destroy each other, and we're going to get two photons. As you know, they're always 511 keV, regardless of the positron energy. They're always 511, and this angle is always 180 degrees. Now, here's a good exam question for you. A high energy positron, let's say this is a high energy positron, maybe 500 keV, hits its electron. Will it annihilate or not? And the answer is no. Only a low energy positron, one that has lost its kinetic energy, will annihilate. And therefore, that high energy positron will just knock it out of the way, form an ionization event, but not annihilate it. And as that positron cools off and loses its energy, then it will annihilate. All of that doesn't take a second, but it's not immediate. Here's a good exam question. What is the energy equivalence of one electron? And you can see here that if two electrons destroy each other, what do we get? Two 511s. That means that the energy equivalence of either one is 511 keV. That is, by using Einstein's equation, if you plug in the mass of an electron multiplied by the square of the speed of light and use a correct conversion factor, you come up with 511 keV. That's the energy equivalence of one electron. Now, this is a pretty complex looking decay scheme. And for right now, I just want you to look at the bolded arrow. This is the only decay scheme that has a broken arrow. This vertical line down here, this is for positron decay. This vertical line, 2mc squared, is the activation energy required to get positron decay. And then the line then goes from right down to left, as we would have expected it to do. And there's your beta plus. Now, in this particular example, it only happened 1.5% of the time, but still it did occur. And you can see that the competing mode here is electron capture. We went from zinc 65 to copper 65 in both cases. We started in one place and ended in one place. So these are competing modes. This electron capture here occurs 53.5% of the time, and this is 45% of the time, and this is 1.5% of the time. And then this transition here gives off a 1.1 million electron volt gamma, which we don't like at all. Not possible to image with it. So but for the beta plus decay, we are going to be dealing with this broken arrow. You'll always see that vertical line down, and then this is your positron line right here. Okay, any positron questions? Okay, the next one is electron capture. Electron capture, I'm surprised it doesn't occur more often than it does, because a nucleus has lots of protons in it typically, but the K-shell electron only has 2 electrons. So there's a disproportionate pull on the K-shell electrons by those protons in the nucleus. I'm surprised it doesn't happen a lot. But here's what happens. Think about this. The proton in the nucleus reaches up, pulls an electron out of its orbital down into the nucleus and captures it. And then a proton combines with that electron and forms a neutron. So that raised the NP ratio. You got rid of a proton, you formed a neutron, and that is often called K capture, but mostly we call it electron capture. And when an electron is ejected, what happens? There's going to be a vacancy. A higher up electron falls down to fill the vacancy. And what's given off? Characteristic X-rays. Characteristic means we can assign a number to it, like that X-ray is 89 keV. Has a specific number, characteristic number. And so all electron capture is associated with characteristic X-rays. Here's your equation. This electron is captured by this proton, forms a neutron. And so this is a completely balanced equation all over the place. And so the NP ratio is going to go up. And here's a generic equation for EC, just like this, really the same as positron decay. This went from N over Z to N plus 1 over Z minus 1, just like positron decay did. And so we're now looking at these 2 bolded lines. And this one, zinc goes straight to the ground state and gives off no gammas, 50%, 53% of the time. But look at this. Electron capture here occurs 45% of the time. And this is an excited level of copper 65 right here. This line is copper 65M. It drops down with this gamma by isomeric transition and forms stable copper 65. So here, these arrows are straight down to the left, whereas this is a broken arrow, and that just differentiates between EC and beta plus. Here's a great exam question. Let's say you have iron 55. Iron 55 decays by electron capture, but it goes straight to the ground state. There are no gammas being given off. Here's your exam question. There are 3 possible answers. Is iron 55 an imageable isotope? Possible answers are yes, or no, or maybe. I've given you enough information to answer the question. Is it imageable or not?
Would it be yes because of the X-rays that are given off?
You are correcto. Very good. There are always characteristic X-rays given off in electron capture, regardless of whether it goes to the ground state in one step or goes through excited daughter. So there are always characteristic X-rays. And if they're in the range of greater than 70 up to a few hundred, we could image it. So the answer is maybe, because we don't know what that energy is. If we knew the energy, we could have said yes, but we didn't know. So it's a generic question about electron capture, and all electron captures emit X-rays. Okay, and the very last one we're going to cover, and we're just going to run over about 2 minutes maybe, and then we'll be done. Isomeric transition is a transition from an excited nuclear state or a metastable state to the ground state. We've had examples before, technetium metastable going to ground. You'll note that there are no changes in A, Z, or N. The proton number stays the same. So what direction are we going to draw the gamma in?
Straight down.
Straight down.
Straight down, right? There's no change. And the parent and daughter are nuclear isomers. And we refer to that metastable state, which means it has a measurable half-life. And here's your decay, just so you don't have to look at technetium again. Cobalt-60 metastable has a 10-minute half-life. It goes straight to the ground state of cobalt-60. And if you wait 10 half-lives, which is 106 minutes, let's say 2 hours, this is gone. And essentially 99.9% is this. And this is a cobalt-60, 5-year cobalt-60 that has been used for decades in radiation therapy departments to perform radiation therapy on cancer patients. Just recently, they converted to X-ray generators, but historically it was always cobalt-60. Okay, now, I'm going to show you what I think is one of the very best physics questions I've ever seen on an exam. I wish I could claim credit for inventing it, but I didn't. But here it is. This is a summary of the arrows for decay modes. I'm going to name a line segment, and I'd like you to tell me, based on just the direction of the arrow, what mode of decay is. Let's start at the right. A, E, E like Edward. What's the mode of decay?
Beta plus. Beta minus.
Minus.
Okay, good. Remember, in beta minus decay, a neutron is converted to a proton. The proton number goes up Y bond. So AE is beta minus. How about A, D like David?
Gamma.
Isomeric.
Good. Yes, it's emitting a gamma, but the mode officially is isomeric transition. AFC.
Electron capture.
Beta plus.
One of you is right.
Beta plus.
Yes, it is beta plus. Remember, beta plus has the broken arrow. A to F is the activation energy, and FC is the positron. So AFC is beta plus. What line is AC?
Electron capture.
Electron capture. And then AB is
Alpha. Alpha.
alpha. And I drew it so that you'll see that alpha is really supposed to be 2 units to the left, whereas this one is 1. It's not exactly in the middle, but you get the point. Alpha is way to the left to anything else. Now, I made a big deal of saying that it depends on what the Z number is. So look at the answer key here. And beta minus, it goes from Z to Z plus 1. IT, no change. Z beta plus, it goes from Z parent to Z of the parent minus 1, as it does with electron capture. And alpha is Z of the parent to Z of the parent minus 2. So hopefully that diagram will clarify for you, if you had any doubts about it, the directions of the arrows in all the different modes of decay. And we're actually right on time. My clock says about 1 minute after 11. And so we're going to stop here. And next Thursday, we're going to cover interactions of ionizing radiation with matter. And then after we do that, that'll take about 30 minutes or so. We're going to take an in-class test on this lesson, on the lesson you'll have first lesson next week, and also all the stuff about modes of decay. So before next Thursday, you might want to look over this lecture on modes of decay, because the test will cover that, as well as the interactions of ionizing radiation with matter. It will not cover the statistics. We already took a little quiz on that. So we're going to stop here. I'll open the floor. If anyone has any question about anything, just please unmute yourself and speak up. Anyone? Okay, very good. Then I am going to say, as always, thank you for your attention and for participating. And I hope you have a good week, and I'll see you 9 o'clock next Thursday morning. So have a good week. Take care.
Thank you.
Thank you.
Thank
Yeah.
you.